before we start with the lecture, I just want to go over this. It seems like there's been a little bit of a confusion on how to choose your topic as a group. So many of you sent me your topic just saying whey protein, casein, or cereal. But what I intended you to tell me as well, so if you want to focus on whey protein, what do you want to focus on? Denaturation, structure-function relationship, bioactivity, allergenicity, fractionation and purification. So you want to select a subtopic. I guess I need to modify this by stating, okay, your topic and your emphasis. So if you go back and discuss with your group member what you want to focus on in terms of a topic and an emphasis out of the listed areas of emphasis, because all of this, we're going to talk about all of the topics in this course and emphasis area. So it will be great to choose that way. The other thing I was going to say, we did lose one more student, so we will have a group of 3 rather than having a person work alone. And that group of 3, actually, I'm going to have to choose for you a topic. And that would be the protein modification, because it's the richest topic to be covered by 3 people. Okay, so the person who lost a partner is you. And then I will have you join another group that will want to focus on protein modification. So you don't have a choice, only yourself, but the other groups, whoever is going to choose protein modification, keep in mind that I'm going to add a group member to your group. Okay? So, with that said, please today, if you could, just at the end of the lecture, talk amongst yourself and email me with, again, 3 preferences. Prioritize them 1, 2, 3, or put them in order of preference 1, 2, 3. Okay? All right. So, hold on, I did not set this up. Okay. All right. So, to continue where we left off, because it was a whole week, so let's do some recap questions, so to get us refreshed in terms of memory and moving on. And since Myson is taking participation, you know all the names?
Okay. I think so. Yeah, Jordan, Sophia, Yuan.
Is it Yuan or Juan?
Juan.
Mm-hmm.
Truthy, Xiao Chen, Myson, Sonia, Claire.
And Farah.
Fair.
Yeah, okay.
I think I have Insane on the list.
Oh yeah, I wrote you.
Yeah,
I wrote
okay.
Okay. So you're good, so you know everybody. All right. What are some nutritional and physiological roles of proteins in food? Some of what we covered last time. Talk to me.
Emulsification.
Nutritional and physiological.
Bodybuilding.
Bodybuilding, yes. Other than that, does it fall under nutritional or physiological?
That's the macronutrient.
Bodybuilding. I don't know, really. I thought it was a category by itself. Huh? Physiological, yeah. Okay, so increased muscle density. Yeah, okay. All right, what else?
We talked about the quality of the, like nutritional is affected by the quality and the digestibility of the amino acids.
Yeah, so the quality of the protein is basically a function of amino acid composition because of the essential amino acid, as well as a function of the digestibility. So digestibility and essential amino acid both fall under quality, and the quantity becomes also under nutritional because you need a certain amount of protein per day. Okay. Other than bodybuilding in terms of physiological roles,
We talked about the method we use, the nutritional thing, how we use Kadal.
no. Yeah, the method for quantification, but for physiological benefits other than muscle building,
Satiety.
satiety. So they have other physiological benefits such as satiety, antidepressant, antihypertensive, antioxidant activity, as well as association. We talked about of phytochemical associations. Some phytochemicals are hydrophobic. They associate with the proteins, especially one example are phytochemicals in soy. Okay, so what are some physical roles? Yeah. So physical roles, we categorize them as color and flavor and structure related. So we have the color. Always when you think about physical, you have to, in case of protein in this case, divide them into these categories: color, flavor, and structure. And under structure, emulsion is one form of structure, gel, elasticity, viscosity. These all gelation, these are all under structure in terms of physical role. Okay, so what are some intrinsic factors that we mentioned in that slide that I told you you're going to see the entire semester that impact protein structure? Fine.
Composition.
Amino acid composition is one.
Source.
The source, that means it's a dairy protein, soy protein, or cereal protein, etc. They differ in structure. What else?
Is that one with molecular configuration?
Yes. Well, the structure is kind of your molecular configuration. It will impact, function, basically. Others, yeah.
We have the sequence and the reactivity of the R group.
Molecular, the amino acid sequence, reactivity of the R group,
Hydrophobicity.
huh?
The
Hydrophobicity,
hydrophobicity.
hydrophilicity, charge, molecular interactions. These are all intrinsic factors. Okay, extrinsic factors. Yeah. Temperature, processing temperature, pH of the environment,
Ionic strength.
ionic strength of the environment, processing, any form of processing, whether we are heating or applying pressure, or we are texturizing by extrusion, any form of processing, any form of heat during processing. Okay, modification, enzymatic modification, chemical modification, other natural mechanism modification. So the list of extrinsic factors, as we said last time, is huge. It surpasses the list for intrinsic factors. Okay, so can you give them multiple examples? Can you give few examples of how a change in protein structure may impact functionality? A positive way and a negative way. Can you think of a positive way? You can participate.
It could impact like water binding if you're exposing hydrophilic versus hydrophobic groups.
Yes. So let's say if you have exposed, you denature the protein and expose hydrophobic group, your water binding might be impacted negatively. And another functionality will impact it negatively by such change is you have reduced solubility. So that is a negative change. But sometimes changing the structure and also exposing hydrophobic groups is beneficial. In which case?
Emulsification of like whey.
Emulsification for whey, exactly. So when you have whey protein, it's a globular structure, it's a very high surface hydrophilicity. When you open it up, you expose some of the hydrophobic interior, you improve the emulsification capacity of this protein because emulsification requires a balance between hydrophobic and hydrophilic groups on the surface. Okay, there are a lot of different changes in protein structure that will impact so many different functionality, and we'll talk about that in later lectures. What is an R group on an amino acid and how it may differ among different amino acids. General terms, not specific. I'm not looking for exact R group.
Side chain.
Huh?
R group is the side chain.
R group is a side chain that is not an amine group, not a hydrogen group, not a carboxyl group.
It might be that aromatic would be hydrophobic
Mm-hmm.
or aliphatic hydrophobic.
Yeah.
Like an R group.
Yeah. Let him answer some.
Determines the polarity of the amino acid.
Say that?
It determines the polarity.
Yeah, it determines the polarity of amino acid because if you have a long hydrocarbon group, it's nonpolar. If you have a charged group, then it will be polar, and so on. It might have a reactive group, like a free sulfide group that will interact. So yes, so different amino acid group differ in the R group, and therefore they differ in their reactivity, their polarity, their hydrophobicity, their molecular interactions, and so on. Okay, I guess we caught up a little bit. Okay, we go back to this as a reminder of the whole building of the entire course. We are here already. We're going to talk about intrinsic factors and how this would be the native form of the protein structure, and how the native later on will be converted into a denatured or modified form due to extrinsic factors, and how that will impact functionality. So this is the entire course right there. But we started off saying, okay, we'll start with intrinsic factor. I grayed out the source for now because these will be individual lectures on different sources. And we started talking about intrinsic factors, and we highlighted that the proteins differ in amino acid composition, sequence as well. So amino acid composition and sequence. They differ in structural configuration due to differences in amino acid composition and sequence. And with that, also they differ in chemical and biochemical properties, mainly hydrophobicity and net charge. Because they're so different, they vary in functional contributions. And they are also, you can add to this, they are impacted differently by extrinsic factors. Because intrinsic factors are different, they will be affected differently by extrinsic factors. We introduced the amino acid basic structure. You have an amine group, you have a carboxyl group, close to neutral, they're both ionized. They will have a net zero charge if the R group is not charged at close to neutral pH. We talked about this being basic. This is acidic, so that's why they act as a buffer, because the basic will resist pH change when you are adding alkaline, so eventually it will give up its hydrogen. And then acidic contributes by picking up hydrogen when you are or providing hydrogen or picking up hydrogen when you're titrating with acid or base. And then we talked about the R group and how it differs and how it will impact all of these characteristics. So we left off at this slide, I think. We talked about hydrophobic amino acids. We talked about the charged hydrophilic amino acids, and we stopped at the polar amino acids that are not charged. So a side note here, I would like you to know the 3 letters for each amino acid. I'm sure you've learned that before, and you also learned the 1 letter. Since I don't know the 1 letter for all amino acids, I don't request you to know them. I only request you to know what I know. So, but most commonly it's the 3 letter that is mostly used for different amino acids. And also you're responsible to know the structures of amino acids. It's very important that you know the structures, because everything in this course is built upon the structures of amino acids. And I'm sure you learned them before in food chemistry and any other place.
Like, that's the question, like how to identify them or like throw them on?
Huh? No, you're going to draw them in an exam. Okay. I already exposed 1 question in an exam. Okay. So, the polar, among the polar, a very unique amino acid is glycine. So glycine is unique and is different from all amino acids. Can one of you pick out why it's very unique, different from all amino acids?
H is more acid.
Huh?
Only have
Yes, Anya?
The answer is there, I think, but it's because the C is
No,
viral.
that wasn't the
Not
answer.
that one? Okay.
Well, of course, it doesn't have, that's one of them. But you were saying,
H has more acid.
so the H here is your R group, which makes this the smallest amino acid. It's the smallest amino acid among all of them, and in structure, this is very important, it has the least steric hindrance because the R group is the smallest, so it will allow maximal rotation when we want to rotate the peptide to form a certain structure. This allows maximum flexibility. So that's what unique about glycine. In addition, of course, because you have two hydrogens, it's no longer a chiral carbon. Okay. The other two groups that are unique also is glutamine and asparagine. And glutamine and asparagine can be precursors to glutamic acid and aspartic acid. So in a protein, you might have glutamine, asparagine, aspartic acid, as well as glutamic acid. But if you treat that protein, let's say you did acid hydrolysis or alkaline hydrolysis when you are determining amino acid composition, both glutamine and asparagine will undergo deamidation, the losing of an amide group. And by doing that, by losing this amine group here and this amine group here, what you end up having is a carboxyl group, and that gives you the glutamic acid and the aspartic acid. So in nature, again, a protein might have both glutamine and glutamic acid, asparagine and aspartic acid, but if you treat that protein with acid or alkaline, then you actually will convert glutamine and asparagine to glutamic acid and aspartic acid. That's why when you determine amino acid composition and you do acid hydrolysis or alkali hydrolysis, you can never determine these as such. They're always determined as glutamic acid and aspartic acid. Good college board question. I just thought of it. Add it to the list, Claire. Yeah. Okay. These two are unique amino acids in the sense they have a hydroxyl groups, or one hydroxyl group each. And these two amino acids are subject to something that you probably already know, post-translational modification. So post-translational modification, that means in the cell itself, they can be esterified. They can be esterified either with a phosphate group or a glucoside group or a carbohydrate group. So in nature you have two types of proteins as an example that are phosphorylated, alpha casein and beta casein, and we'll talk about that when we talk about dairy proteins. And also in nature you have glycosylated proteins such as kappa casein. Another example is a protein in soy, beta-conglycinin, and we'll talk about that when we cover soy. So they are naturally occurring due to post-translational modification and due to the presence of these hydroxyl groups that can be esterified. Let's see what else is on there. Okay, this is very important. The cysteine, it's really important in terms of stabilizing a protein structure because you can form a stable tertiary structure if you have sulfidyl groups in there. They can form disulfide linkages and have a very stable protein structure. Or if you have free cysteine groups, can promote polymerization upon processing of the protein. So, for example, gluten network formation, one of the forces that you transfer gluten forming proteins into gluten is disulfide interchange. So when you knead the flour and water, what you're doing is you're denaturing gliadins and glutenins. They're opening up, they're exposing sulfide groups, they're forming polymers, and you get that viscoelastic protein formed, which is the gluten. And that's just one form of different interactions that cause the formation of gluten. So that's one example of what the importance of this group. And this is an illustration that you have cysteine. So now this is where the funny part is. Can you pronounce this versus that?
Cysteine versus cystine.
Mm-mm. Cysteine versus cysteine. There's no E-E. Cysteine versus cysteine. Okay, so cysteine is basically a dye. Cysteine. So it's the oxidized form. And then, so this is basically an oxidation reaction where you get the disulfide bond formed. But this bond can be reduced if you add a reducing agent. And oftentimes you add a reducing agent during the formation of the dough, for example, because you don't want really a very strong elastic dough. You want to make the dough a little bit more viscous than elastic for different applications. For example, pita bread. You don't want it to be so strong that it will not form a round, flat dough. You don't want it to shrink back, so you might want to reduce some of the thiol groups or some of the disulfide linkages in case you have really a type of wheat that is very strong type of wheat, and then you only have that to use for different applications, so you can add reducing agent to change the elasticity of that particular flour. That's one example. Another example for reducing agent is oftentimes you have large proteins and you cannot see them on a gel, on an electrophoresis gel. So you want to break the disulfide bond so that you can see the individual molecules. So you add a reducing agent to break up the large polymer. So there are different applications where reducing agents are added. Reducing agents can you name some from your process? Beta-mercaptoethanol, but that you can't add in food, right? DDT, is there a food grade DDT? Not?
There might be. I've not used it.
Yeah. What is a food grade? Sulfites. So you can use sulfites, you can use actually cysteine, certain concentration of it, you can use glutathione. So there are some food grade reducing agents that you would use when you want to apply a reducing agent for food application. But when you're using it for research purposes, yes, you can use beta-mercaptoethanol, DTT. DTT stands for dithiol. Huh?
Dithiothree.
That. Okay. All right. So I guess with this we concluded the different types of amino acids and how they vary in structure and gave few examples. But throughout the semester we're going to go back to each amino acid. If we're talking about modification, we're going to talk about which amino acid got modified because of the functional groups they have. So this will come back to us throughout the semester. Another characteristic of amino acid is the acid-base properties of the amino acids. One common thing that you will hear about is pKa of the functional groups. Okay? So if you have an amino acid such as serine, for example, this is just an example, you only have 2 pKa's because your R group does not have another ionizable group. So you only have pKa1 and pKa2, or sometimes they call them pKa and pKb. Okay? But oftentimes they're just referred to as pKa1 and pKa2. So the pKa1 is for the carboxyl group and pKa2 is for the amine group. from what you know in your chemistry, when the pKa value is acidic, is low, this means it's for an acidic group. So this means that at pH of 2.21, half of the carboxyl groups are ionized and half of them are having their are protonated. Below pKa 2.2, you start having most of the carboxyl groups as protonated, and then your net charge becomes positive. As you reduce the pH below pKa, your net charge is going to start to be positive. Now, looking at the other pKa value, which is for the amine group, any value or pH below 9.15, most of your amine group are going to be protonated. As you start increasing the pH, this amine group is going to go, okay, I'm going to give you my proton. Now that you're insisting and giving me base, I'm going to give up my proton, and then this loses charge, and most of you, or all of your carboxyl groups are going to be negatively charged. Then you will have a net charge of -1, if we're just looking at one amino acid. Okay, but it gets complicated from here. Okay, you need to memorize all of these. No, you don't need to memorize them, but this is what you need to know. You need to know that there is a pKa3, and this is for the R group. So if you have an ionizable group, amine or carboxyl, then you will have a third pKa. So obviously the basic ones are, what is that? Arginine, lysine, tyrosine, and there should be another one. So arginine, histidine, where's histidine? Oh, it's 6. Wow. Right? And cysteine too. So this means that cysteine and tyrosine, as we talked earlier, they're ionizable at high pH. But so arginine is basic, lysine is basic, histidine is basic too, but it has a lower one because I think this would be due to the fact that it is a tertiary amine. I don't have it on in this slide, but if you go back, it only has NH plus. So the nitrogen has three bonds already, so it has NH plus. So it's not as basic as the other ones are. The others have NH3 plus and NH2 plus. Like lysine has NH3 plus is a primary amine, and then the arginine is a secondary amine. But it has 2 amine groups in their R chain. So that would be why it's different in the pKa values. But what I'm pointing out too is that if you have a functional group that is ionizable, then there is another pKa and we call it pKa3. And then aspartic acid and glutamic acid are acidic. This is because of the extra carboxyl group. Okay. So when you are at the isoelectric point of a particular amino acid, then you'll have a net charge of 0. So you will have all of your groups are ionized, so they cancel each other in charge. And the way you calculate isoelectric point is mathematically by adding the 2 pKa's and dividing by 2 to get the isoelectric point of an amino acid. But in the case that you have a third functional group, then the way you calculate the pi is by adding the pKa 1 and 3 for acidic amino acid and dividing by 2, and pKa 2 and 3 of basic amino acids. And if you do that for all of them, you'll find out that these are calculated that way. All right. So this is just to bring back the fact that this is, since it's a buffer, proteins are considered buffer, so they follow the equation of the Henderson-Hasselbalch equation in terms of pKa and pH relevance and the concentration of acid to conjugate base. So again, at the isoelectric point, you have something that we call Zwitter ion, or an ion that total net charge is 0. And then as you increase the pH, you start getting negative charge. Above pKa2, you will have mostly negative, and below pKa1, you will have mostly positively charged groups. Okay, so this concludes the first lecture from last time. So now if you can look at your slides for today's lecture, we'll start here. I did make some edits this morning, so if you printed them out yesterday, there might be few changes, but the updated version is on Moodle. Okay. What would be your answer for this? Yeah. So all of the above. So of course, we will talk a lot about how the hydrophobicity impacts structure. And obviously, if you have more hydrophobic group, you have more active emulsification, so you can bind or interact with fat, or you have interactions with fat, not you personally interacting with fat, but. And then, of course, if you have high percentage of hydrophobicity, for example, corn protein is more than 40% hydrophobic amino acid, so their solubility is terrible. Okay. What about this one? Any idea? A vague idea? I don't expect you to know this, but any guesses?
B and C.
So we have so far A and C, B and C. Everybody's liking C. Yeah? Who said A and C? Yeah? It's A and C. Okay, so disulfide linkages stabilize protein's tertiary structure. Hydrophobic interactions are the main driving force for the formation of the secondary structure, while the secondary structure is stabilized by hydrogen bonding. So this sounds like a puzzle, but we'll talk about that later. So now you know that amino acids, you have hydrophobic and you have hydrophilic, and in one protein you have a combination of both. So proteins naturally exist in an aqueous medium within a cell or what have you. So because they exist or they are formed in an aqueous medium, so they assume a structure where the hydrophobic residues are not so much in contact with water, because hydrophobic residues are not liking water. So they tend to hide away from it, and the way they hide away from water is by associating themselves with other hydrophobic groups. So they will find another amino acid like them or another functional group like them and associate to hide. So your protein starts folding in such a way that the hydrophobic groups become in the inside of the protein or the interior moiety of the protein. And then the hydrophilic groups, they don't care, they stay exposed to the environment. But of course there are cases where it's not always this way configured. We'll talk about these cases later, but in general terms, your hydrophobic amino acids are going to hide from water, your hydrophilic amino acids are going to be exposed to water, so you form these structures of the protein structure where the inside is mostly hydrophobic. So, let's complicate your lives a little bit. You like the free energy concept? No, I didn't think so. But anyway, so we explain hydrophobicity in terms of free energy concept, or the change in energy when the protein is transferred from ethanol, which is an organic solvent, into water. So when you take the protein from an ethanol and put it in water, there's going to be change in energy, in free energy. Okay? That's in simple terms. And that change in free energy is equal to the chemical potential of interaction of amino acid with the organic solvent and its chemical potential of interaction with water. So interaction with organic solvent minus the interaction potential or chemical potential of interaction with water. So if the change in free energy from ethanol, due to transfer from ethanol to water, is positive, then the protein or the amino acid is hydrophobic. Because you have more interaction with the organic solvent, then you will have a positive value. You will have a higher chemical potential. Whereas if you have a higher chemical potential for interaction with water, then you get a negative value, then that would mean it's a hydrophilic. With the exception, there's always an exception, of lysine. Why is that? It's because look at this lysine. Although you have this potentially ionizable group, you have a relatively long chain of hydrocarbons, which makes this amino acid liking more ethanol than water, just because of the nature of the R group. Now, you can also mathematically calculate the hydrophobicity of the side chain individually, not just looking at the amino acid as a whole. And the way to do that is you take the change in free energy for glycine plus the change in the free energy of the side chain will be the total free energy of that particular amino acid. Why is that? Because if we take this portion, it's equivalent to a glycine, and if we take this portion, this is your R group, basically. So if we look at valine, this is valine example, this is your glycine portion, and this is your side chain. If we know the glycine delta G, then we can determine the side chain delta G for side chain. And then we can determine whether or not it's hydrophobic. Okay, so there is a table in the chapter that I have on Moodle. Just look at it, just FYI. I don't expect you to know the numbers, but by looking at the table and then going back to the amino acid structure, you'll go, okay, so these are hydrophobic because, yeah, it makes sense by looking at their delta G. Okay. So far we did acid-base properties, hydrophobic properties. Let's look at chemical reactivity, which is very essential in the protein chemistry world because of the fact that each of these groups, whether the amine group or carboxyl group or R group, if they have a function, especially the R group that has a functional group, will allow them to interact in such a way that impacts not only structure but function. Okay. So the reactive groups in an amino acid, you have of course the amine group and the carboxyl group. So amine group, carboxyl group. The amine groups and carboxyl groups often are part of hydrogen bonding. They take part in ionic interactions. If they are ionized, they can be modified, and we'll give few examples about how you can modify an amine group or a carboxyl group, the modification can lead to a quantification assay, or the modification can lead, actually, if you want to modify via chemical modification, you can change the structure, change the function. And I'll give few examples now, and later when we cover chemical modification at the end of the semester, we'll remind you of those as well. Sulfidyl group, we talked about it being very active, and we gave few examples already. Phenolic groups, there are, first of all, they're hydrophobic, so they interact via hydrophobic interaction. If they're present, they promote hydrophobic interactions. And not only that, they absorb light, so they are used for quantification purposes. And then we talked about the hydroxyl groups in serine and threonine, and these hydroxyl groups, along with tyrosine in this case, they can be ionized. These, particularly serine and threonine, can be esterified. So they can be modified or esterified. The thioester also can also react with different groups, but it's not a focus in food proteins. Not a lot of modification is based on the thioester group of methionine. The imidazole group of histidine also is a group that can be modified or can react due to the presence of amine group. Same with guanyl group for arginine. Arginine, histidine. So reactivity of these group and changes due to the reactivity of these group impact the hydrophilic and hydrophobic nature of the protein, and by doing so impact the functionality. This is a table from actually Untitled Chapter on protein, the 3rd edition. The 4th edition, I believe the table is table 5, but I looked in both editions and I found they have errors in the structure. So I thought it's just in 3rd edition and they have corrected it in the 4th edition, but when I looked again, and so there are errors. So here it's a B, it shouldn't be a B, and this is not a double bond. There's a sulfur group, and this is not a double bond. Here there's an OH. And in this case it's thiolation, so you react the protein with a group that has a sulfur, and then thiolation means you have a sulfidyl group added to your protein. So you're adding a reactive group for a purpose. So you're adding a reactive group probably because you want to induce polymerization. You want the protein to polymerize. So you induce a reaction that will add a sulfidyl group. And thiolation is specific for amino groups. So here you have the amine group of a protein or an amino acid, and it reacts with this compound, and then you will end up having a modified protein with an additional sulfidyl group. Succinylation and acetylation are also chemical modification. In acetylation, the amine group react with acetic anhydride, and then you end up having blocking a positive charge. So by blocking a positive charge, you are increasing the net negative charge of the protein. Because you're eliminating a positive charge, then the protein will be less positively charged and possibly increase the net negative charge, or just reduce the charge as a whole, depending on the type of protein. Remember that different proteins will have a different, or modification will have different impact on different proteins. Succinylation, in this case, you add a succinic anhydride, and with that you're adding a carboxyl group, then you're increasing the net negative charge. So in one case you're eliminating a positive charge, and by doing so you either reduce the net positive charge or you increase the net negative charge depending on the original charge of the protein. In succinylation you are actually increasing the negative charges on your protein. In both cases, you're impacting the charge, and by impacting the charge, you are changing the functionality, either making them more soluble or, for example, making them better emulsifiers. So we'll talk more about chemical modification in the modification section of the class, but here I'm just highlighting that the amine groups can react to different groups to get to different outcomes. Here's an example for reaction with sulfider group. So in either you have an oxidation, obviously, and we talked about that, or you promote blocking of the sulfider group. So if you don't want to have polymerization happen in your protein, you reacted with a compound that will result in blockage of a free sulfider group. Then you don't have a reactive group anymore, then you reduce the potential of polymerization if the final product you don't want a polymerized protein. Okay, I feel that I'm talking too much, you're taking notes. Do you have questions? Or would you like me to repeat any concept? It's okay to ask me. Yeah.
Both acetylation and
Succinylation.
they both decrease charge because one is.
Actually, one will decrease, one will increase. One will, okay. Again, it's a good question. Let me illustrate. So some proteins in egg are positively net charge of positive in egg protein. Dairy protein, for example, whey has a net, or casein has net charge negative. If I'm looking at an egg protein that has a positive net charge, so can you see here if I write? So if I have a plus 11 as a net charge in a protein versus I have a minus 20, or let me make it one of the whey protein, membrane whey protein is minus 18 charge. So if I'm looking at egg protein and I do acetylation, that means I'm reducing the net charge. It becomes plus, let's say, 8 net charge. By doing so, I might enhance emulsification. I'm making it less polar. I'm increasing the balance of hydrophobic to hydrophilic. I'm making it good emulsifier. Here, I'm adding negative charge by adding, by succinylation, I'm adding a negative charge. I'm adding a carboxyl group. So this might become negative 25. By doing that, what am I doing? Increasing solubility, right?
So the lower the net charge, the better solubility.
This is a high net charge, but it's a high net negative charge. This is a high net charge, but positive charge. So the high can be negative charge or positive charge, right? Hmm? Do you get that?
Kind of.
Where's the hang up? So the net minus 25, you have higher density of carboxyl groups. And higher density of carboxyl group means high negative charges. Whether you have high positive or high negative, you have better solubility.
Okay, so it can increase solubility either way.
Either way, because you will have more interaction with water. Whether you have more negative charge or more positive charge, you have a charge.
Yes.
And water, you have the H2O. So here can interact with the negative, and this interacts with the positive,
Okay. Yeah.
right? So water can interact with both.
Yeah.
Good question. Any other question? I like this question. No? Moving on? Okay. Chemical reactivity can also be beneficial for quantification. So let's say we are determining the amino acid composition. We break up the protein into single amino acids, then we want to quantify it. So we separate the amino acids using chromatography, and then we want to look at the amount of each amino acid. And if we're using chromatography and absorption, linked to an absorption detector or light absorption detector, not all amino acids are going to absorb light. Only 3 amino acids absorb light. tryptophan, tyrosine, and phenylalanine. What about the rest? So the rest, I need to make them interact with a compound that will produce another compound that will allow measurement of absorption of light. So in this case, in this example, you have ninhydrin. The ninhydrin will react with the amine groups, the free amine group of an amino acid. And if you follow the color codes, you will see where each group went in terms of the chemical reaction. And then it's a series of reactions actually, and you end up with a product that will absorb at 570 nanometer, except for proline and hydroxyproline defiant amino acids, will absorb at 440 nanometer. But anyway, with this reaction, you generate a compound that absorbs light for all amino acids, not just those 3 amino acids that originally absorb UV light. Here's a reaction that we often use not just for quantification of free amines, but also to determine degree of hydrolysis, which is very important, and we will talk about it when we talk about protein modification by enzymes. Degree of hydrolysis is how many or what percent of peptides we broke in a particular protein. And in order to determine that, the more peptides you're going to break, the more free amine you're going to release. And the free amine, or the primary amine in this case, will react with OPA, a reagent, and in the presence of a reducing agent, will give you a compound that fluoresces. And that you will measure absorption, fluorescence at, this is the excitation and this is the fluorescence relaxation. So always with fluorescence, you have to have an wavelength for absorption and then wavelength for detection of fluorescence. Okay. Another quantification can be done with fluorescimine. Again, there is a reagent that will interact with primary amines, and then you get again fluorophore, and you measure fluorescence. Okay, so these are examples of when you use reactivity for quantification purposes or any analytical measurement purposes such as degree of hydrolysis. And here we go. We should put a sign on the door. They left already?
Yeah.
They heard my voice. Okay. All right. So moving on. Any questions about reactivity before I move on? Okay. And please remember, we're talking about reactivity in terms of just amino acids, but the same reactivity can occur in a protein when that amino acid or that reactive group is present. All right. Moving on, let's build the structure of the protein. I promise this is the last lecture that I'm going to talk pure chemistry, and then we'll start with more applied examples. I'm trying to give you applied examples, but we need the chemistry to get that applied. Okay, so let's build that structure. So you will hear me talk about primary, secondary, tertiary, and quaternary, and I'm sure you've heard about these before. And the primary structure is basically just the sequence of your amino acids. Okay, so primary structure is that linear sequence of your amino acid, but obviously a protein is not linear. It will fold on itself to give you secondary, tertiary, and sometimes quaternary. But let's start with the primary and what forms your primary sequence. What links amino acids together obviously is your peptide bond, and the peptide bond is a bond between a carboxyl group of one amino acid and the amine group of another amino acid. So basically this is your chiral carbon here. This is the carboxyl group attached to the chiral carbon. This is the amine group of the second amino acid attached to this chiral carbon right here. Okay, so that and that is a peptide bond, and it's a condensation reaction because once the bond is formed, you're losing water. Okay, so when you break the peptide bond, it has to happen in the presence of water, obviously, not on a dry basis, because when you break the peptide bond, you need water to go back to the original amino acids. Okay. So for one peptide bond, 1 molecule of water is needed. Either to break it, you need 1 mole of water to break one peptide bond, and you release 1 mole of water for breaking of 1 mole of a peptide bond, or 1 molecule for 1 peptide. So this is the L configuration. So here you have the L because the amine group is on the left, and normally we call this the amino terminus, and this is the carboxy terminus. So you'll hear this terminology a lot. N-terminal sequencing, for example, you're going to hear about that a little bit. N-terminal sequencing, meaning you're identifying the sequence of the protein, starting from the N-terminus of the protein. Okay, so these are terminologies that you will hear later on. Another fact to keep in mind is that an average molecular weight of amino acid is 135 daltons. This is the average. Obviously not all amino acids have the same molecular weight, but this is the average. And proteins range in molecular weight, but most of the protein, or most of the food proteins that we'll encounter, have a range of 20 to 100 kilodalton, or 20,000 to 100,000 dalton. So your unit, you're going to either see kilodalton or you're going to see dalton as a unit for molecular weight for proteins. So what does the linear sequence, what do the linear sequence and length determine, not determine? What do they impact? The sequence and the length. So the different amino acid in sequence and how big of the protein it is. What does that impact? Before that, before we get to solubility, it will impact solubility, but before that, structure. So the linear sequence is going to have a direct bearing on the structure of the protein. Fun fact, chemistry facts about your peptide bond. You're gonna love this. So you have three unique bonds that will impact the folding of the protein. So the peptide bond itself, that molecular bond here between the carboxyl group and the amine group, is your omega bond. Omega angle, I'm going to say, and it's a 6 degrees angle, and this is a very rigid bond. It's not very flexible. The peptide bond is not, because it assumes a partial double bond nature. Why it assumes a partial double bond nature? Because electrons from this oxygen here and nitrogen here can form a partial double bond and then go back. So the electron movement here, so it has this partial double bond nature, and because of that makes it a very rigid bond. It's not very flexible. Okay. So the two other bonds that are really important for the flexibility of the peptide chain is the phi and psi. So the phi angle is the angle, or is the angle of the bond between the chiral carbon and the amine group, and the psi is between the chiral carbon and the carboxyl group. Okay. Theoretically, they have flexibility. Theoretically, they're flexible. There's a rotation going on. There a stretching and bending of the bond that happens theoretically freely. But what makes that not true in practical terms? So theoretically, you can look at these bonds and say they can bend, stretch, rotate freely. But what would prevent them from doing that?
The other amino acids is floating around them.
The R group.
Oh.
The bulkiness of the R group will prevent them from having a rotational freedom. So theoretically they have 360 rotational freedom, but the rotational freedom is determined by the R group of the different amino acids in the sequence or in the proximity of these two bonds. So the rotational freedom then affects what? If I have rotational freedom and if I don't have rotational freedom, yeah, what does that impact? The structure, the conformation. So we're going to see that there are amino acids that we call them secondary structure breakers, like alpha helix, for example, beta sheet will be broken if there is a proline, for example, because they're rigid, they don't have the flexibility to form a helix or a sheet. So the rotational freedom is affected by the R group, and the smaller the R group, like glycine here, you have H. Glycine has the maximal flexibility, or allows the peptide, if there are a lot of glycine, you have a lot of flexibility, because these bonds have more freedom to rotate, to bend and stretch. Another fact about the peptide backbone, it's a series of chiral carbon here, this chiral carbon, carboxyl group, amine group, and another chiral carbon. This is a one peptide unit. From this chiral carbon to this chiral carbon is a one peptide unit. So this is a peptide unit. This is another fact. And like I said, proline is the most rigid. Why? Because the R group, look at that, it's linked to this amine group, so it's not free. So this bond here is not free to rotate because this amine group is linked to the R group. So this is gives the backbone rigidity. So, and it's known as, its common slang name is secondary structure breaker. That's the reputation of proline. I didn't give you a break. I didn't notice the time. I love the subject so much that time just flies for me. Take a couple of minutes to break. You can step out and do whatever. You guys can remind me, it's like, give us a break. missing one person still. Yeah. Hmm.
So much.
Pretty old.
Oh.
No, we shouldn't do that. I'm trying to prevent food waste.
What it's super good.
Oh, I know where it is.
Yeah, mixed green. Their mixed green salad is really good. I live like right next there. Oh, really? Yeah. I just went there. You can't do any reservations. Sign up for Macau's email thingy and you get a free burger for your birthday.
But it's
Oh,
over
damn.
there.
Sorry.
What are you
Yeah,
talking
it's
about?
Another. No, for 60 days, yeah. What? You'd have to wait another 360 days. Make a birthday.
Big,
Don't
no,
change
I
your
can't
ID.
do that.
My
My moral.
birthday.
Can I be like, I just, I don't know, like.
I'll put it here. Oh, it's not so bad.
So do you have any questions while waiting for Chao Shen? No. No questions? You're enjoying the topic, right? It'll get better. Well, we need this to understand the better stuff.
Bye.
How do you like that?
I don't like it. It's good.
You don't like it, but it's good for you?
Yes.
That's very committed. You're very committed.
I tried to. Look at how big this is.
You are really committed.
I know.
Okay. All right. So the peptide bond can be in the trans or cis orientation in terms of the alpha or the chiral carbons. This is the native form, the naturally present form. This is upon any processing or heat treatment. Some of the trans configuration can become cis configuration. However, this generates a lot of hindrance, steric hindrance, especially when you have the R groups bulky. If you have this orientation, then it's not a happy state for the protein. In terms of protein, because it's such a unique amino acid, it doesn't matter whether it's trans or cis. It doesn't matter in terms of happiness of this bond. And often when you are processing, the protein can change into cis configuration. Yep, I guess that's what I just said. Okay, so we formed the bond, we can break the bond. So the bond of the peptide bonds can be cleaved either chemically or enzymatically. So chemical cleavage is either alkali or acid hydrolysis. So with heat. So alkali or acid hydrolysis with heat, and often this hydrolysis we usually do it, like I said earlier, to determine composition of amino acid in a protein. The drawback of acid hydrolysis, if you're carrying out amino acid composition and you're using acid hydrolysis, you are destroying tryptophan and cysteine. To prevent this destruction of cysteine is usually you convert them to cystic acid. So there is an acid that you add, formic acid I believe, and then that would convert cysteine to cystic acid, and then you can quantify them. In terms of tryptophan, oftentimes they run the analysis twice with acidic hydrolysis and basic hydrolysis so that you can detect tryptophan. And like I said earlier, acidic and basic hydrolysis will result in conversion of asparagine and glutamine to aspartic and glutamic acid respectively. So you cannot really quantitate asparagine and glutamine as such in terms of composition. So protein peptides can also be hydrolyzed by enzymes. So there are enzymes that are specific enzymes. We call them, well, they are specific enzymes, and there are enzymes that are non-specific, and usually they're referred to as peptidases. So if you hear the word peptidases or the enzyme name peptidases, it means it's an enzyme that is non-specific and cleaves off peptides, any form of peptide, regardless of the type of amino acid. So a very specific enzyme example of that is trypsin, and I highlight that because I think one of the problems of, or probably previous exams gives that as an example enzyme. So it's specific, meaning it recognizes peptides where you have lysine and arginine. So if you have a lysine or arginine, it cleaves after the carboxyl group of the lysine or arginine. So it's right there. So lysine arginine breaks after the carboxyl group of the lysine or arginine. So that's how specific this enzyme is. For example, subtilisin, it's a very has very little specificity, so it's a peptidase again, and it is a microbial source. So there is two different examples. Obviously, there are a bunch of different enzymes, different specificity, and sources, and working range in terms of pH, temperature, conditions. Okay, so that's your primary structure, that you have the sequence now. But proteins transition from a linear polypeptide chain into a folded structure, and it does that because of two concepts: the steric strain concept and the free energy concept. Because of these two concepts, the protein is never in a linear, exists naturally in a linear configuration. So the steric strain, you don't have the rotation, you don't have 360 rotations of all the bonds because of the R group. We already said that. And stretching and bending of these different bonds cause chaos, free energy. So a lot of energy in the system. And also folding avoids conformational changes. So you have steric hindrance, you have free energy, and you have if the protein folds, you stop that movement and change in structure. So looking at the free energy concept, again back to the delta G that you all like. So you have this amino acid and you have all of this movement and all of these different angles or bonding that's going to stretch, bend, rotate. There's a lot of chaos going on. So we want the most stable form is the reduced chaos form, right? So you are stable and happy when there's not much chaos in your lives. Same with here. You have a lot of energy. The protein is not happy. There's a lot of chaos. So the most stable form is the least free energy form. And in order to reduce the free energy, bonding occurs. Okay? Bonding within the protein sequence. And when bonding starts forming, you are containing the energy in molecular bonds. Okay? So by containing the energy in molecular bonds, you are left with free, minimal to no free energy. Then that's the most stable form of your protein. You don't have chaos. So looking at the terminology here, so this is change in free energy. This is delta H is enthalpy, which is the amount of contained energy in the molecular bonds. Delta S is conformational entropy, in other words, the chaos. Okay? So when bonds are formed, you have a lot of contained energy and not much chaos. But if few bonds are broken due to any processing or any modification that you're doing, if few bonds are broken, you're going to have a sharp increase in entropy. You're going to have a change there. With that, you have a sharp increase. This becomes larger than this, and then you'll have a negative delta G. And when you have a negative delta G, that's, we call it spontaneous denaturation occurs. Spontaneous denaturation. So denaturation is a change in the native configuration of your protein. So when we have chaos, this value increases, this becomes negative, you have a denaturation. Okay? The folding, again, I'm just emphasizing, the folding is based to contain the energy through molecular bonds formation. And we'll talk about molecular bonds formation in a minute. Okay. So just let me go back a second. So here's your primary structure. It falls into secondary structure. This is an alpha helix. It can form into a beta sheet or random coil configuration. And this is a tertiary structure where it is coiled into either a globular form or another type of form that we'll talk about later. And a quaternary structure when you have more than one molecule of a protein associate together. And we'll give examples of that later. Okay. So what is the role of hydrophobicity and water in the folding of the protein? We talked about this a little bit earlier. So what did we say about that?
So the hydrophobic proteins in water will fold inside.
Hydrophobic amino acids?
Yeah.
Okay. So let's look at that. So what happens here, this is very important, this is the driving force of the formation of the secondary structure. So what happens here, like I said earlier, the hydrophobic groups are going to orient themselves towards each other and hide from water. So they are start to interact via hydrophobic interactions. So this amino acid here and this amino acid are interacting via hydrophobic interactions. And because they are dominating this space in the inside, they're kicking the water molecules out. Most of it, at least most of the water molecule out. By doing so, they can form hydrogen bonding. Because if you have water inside, water is going to compete for hydrogen bonding. Because, you know, it's excellent hydrogen bonding molecule. You have the oxygen, you have the two hydrogens can form hydrogen bonding. Hydrogens here can form hydrogen bonding with another electronegative, and the oxygen will form hydrogen bonding with a hydrogen attached to an electronegative atom. So basically, by moving the water out, you're allowing the groups within the amino acids to form hydrogen bonding. So this is the stabilizing form of the secondary structure. So that's the first step from moving from a primary to secondary structure. The hydrophobic groups are driving that movement. Start off with hydrophobic interaction containing some of that free energy, allowing hydrogen bonding to occur, containing more free energy, and a step forward towards stability or formation of a stable structure. Okay, again, remember we're containing the energy, we're increasing this and decreasing this as bonding start to occur. We're decreasing entropy, we're increasing enthalpy and decreasing entropy. Yeah, increasing enthalpy and decreasing entropy. Okay, questions? All right. Alright, let's introduce the different bonds. And here's where I made a change depending on when you printed. Instead of a dipole, this is in fact hydrophobic interactions here. So if you have printed, if this says dipole, make sure to correct that. Okay, so this is a portion of a protein, let's say, and you have amino acids, you have different functional groups, and let's define the type of molecular interaction within that protein based on the different functional groups. So what is commonly known as van der Waals interaction basically mostly are dipole-dipole interactions. And dipole-dipole interactions is basically when you have two groups, similar groups, that share electrons, and you have kind of a clouds of electrons that are shared between two functional groups that have a dipole moment. So these are weak bonds, but they're additive. There are a lot of them within the protein. So although they are weak, they are additives. They contribute to increasing the enthalpy. Okay? They contribute towards the stability of your protein. Okay. And in order for the dipole interaction to occur, you need specific distance, and the distance is 6 angstrom. The degree should be on top of the A for the angstrom unit for the distance. Other type of interaction is your hydrogen bonding interaction. So in here you have your hydrogen interacting with hydrogen or linked to an electronegative atom interacts with an electronegative atom. So the electronegative atom can be nitrogen, oxygen, or sulfur. Okay. In order for this interaction to occur, you need to have a distance of at least 2.9 angstrom. And like I said, the hydrogen bonding are the main type of interaction stabilizing secondary structure, mostly in alpha helix and beta sheet. And these amino acids contribute the most to hydrogen bonding: threonine, serine, aspartic acid, and glutamic acid. Next, you have electrostatic interactions. So you have electrostatic, either it's going to be an attractive force or a repulsive force. So when you have positive and negative, obviously it's an attractive force. And most of the proteins that form electrostatic interaction, or amino acids functional groups, would be that of arginine, histidine, lysine, aspartic, and glutamic, due to the fact that they have additional either hydroxyl amine group or a carboxyl group. So the effect of water, I have a question here. If you have water in the system, obviously you will have water in the system. Depending on the location of the water, the presence of water limits repulsion. So if you have two positive charges next to each other and there's a water molecule in between, it prevents the repulsion. Additional to arginine, histidine, lysine, aspartic, and glutamic, you have cysteine and tyrosine that will be ionizable as well, especially when they are at high alkali pH. They become negatively charged, then they can contribute to ionic interaction as well. So hydrophobic interaction is, like I said, it's important. It's the driving force of the folding of the protein and the formation of the secondary structure. And they occur obviously between groups that are hydrophobic, either phenolic groups or just nonpolar group in close proximity. Okay. Last is the disulfide linkage. This is the strongest bond because it's a covalent bond, so it contains the most of the energy. and provide the highest stability for your protein. So the more disulfide linkages you have, the more stable that protein is in its tertiary structure. And the disulfide linkages again can occur intermolecularly within among different protein molecules, or intra within the molecule itself. There's something here you will hear, or you will learn about a little bit more in different lectures: disulfide interchange. Sometimes disulfide interchange, just to introduce this topic. So if you have a protein here stabilized by disulfide linkage, and it does have a free SH group, and then you have another protein here that is stabilized by SS linkage group. This SH group is a reducing agent. It's going to break this bond and form another disulfide linkage. So instead of this is SS, it might form SS here between the two proteins. So that's what we call disulfide interchange, because if you have a free sulfide group, interchange can occur. If you don't have a free sulfide group or any form of reducing agent, there's going to be no interchange, because you need a reduction to promote another oxidation reaction. Okay, so this is an important table. You can put a star on this slide. Okay, it shows you the different types of bonds we talked about. Again, van der Waal or dipole-dipole would be, well, dipole-dipole is under van der Waal interactions. So you can see here that in this table you have the energy that is contained in these different bondings. So the highest energy, like I said, is the covalent bonding. The SS linkage contains the most energy, and followed by electrostatic, hydrogen bonding, hydrophobic, and the least is the van der Waal. Next, that is important here, which functional group is involved in that? Obviously cysteine here. Here you have any group that has an electronegative atom that will react with a hydrogen attached to another electronegative atom. And then here the hydrophobic interaction, any amino acid that is hydrophobic will be involved in that. Electrostatic, those groups that can be ionized, and van der Waals, any groups that can form dipole interactions. So disrupting solvents, this is important. What breaks disulfide linkages is a reducing agent. We talked about that. And what breaks hydrogen bond is urea, detergent. So urea and detergents like STS, for example. Heating will break hydrogen bonding, and we'll talk about that when we talk about conversion of glycogen to collagen, collagen to gelatin. So how the impact of heating, how does it impact hydrogen bonding? And then hydrophobic interactions, again, detergents, organic solvents. Organic solvents break hydrophobic interactions. Do you know why? On what basis? They are hydrophobic, so the hydrophobic components, this is a hydrophobic media, I'm going to open up and interact with the organic solvent rather than with another amino acid in the protein. Electrostatic interaction are affected by pH, so if we change the pH, we're going to change the charge density. Also, if we have ionic, or if we have salts, or we have more ions, the ions are going to shield other charges, so that will impact electrostatic either repulsion or attraction. Enhancing conditions, cooling will enhance hydrogen bonding, whereas heating will enhance hydrophobic interactions. Okay, So this is a very important table, will help you understand different mechanisms that we talk about later. So make sure you learn this table. I thought I was done with the delta G. We have more delta G here. Okay. So I think I already talked about that. When delta G is positive, you have the most stable native state where all the energy is contained. The delta H is the summation of all molecular interactions. And delta GD, it's the change in energy that will cause denaturation. Okay? Change in free energy that will result in denaturation. And look, it's very small. It's 20 to 85 kilojoule per mole. Is a small amount. Is equivalent only to 1 to 3 hydrogen bonds, will result in excessive or spontaneous denaturation. Why is that? If you remember me saying few bonds can break, then chaos will break loose. It's kind of a chain reaction. You break few hydrogen bonding, protein will open up, then you will have larger distances between the functional group, then no more ionic interactions can occur. And then more interactions will be broken, and then denaturation occurs. So it really starts with a very small amount of energy that you give to break few bonds, then it becomes a spontaneous chain reaction for denaturation. Sometimes you want to induce conformational change for certain reactions to occur. One important example is you change the conditions or the environment to allow substrate to bind to an enzyme. When you change, let's say, pH, or you change salt concentration and temperature, you change the ionization state, you change the configuration, and then an enzyme reaction can occur. So you actually, sometimes you want to induce conformational adaptation. Sometimes you want structural stability. That's why some enzymes are stabilized by disulfide bonds, so they can endure a high temperature, long time at a certain temperature without being denatured. Because if you have a lot of disulfide bonds, then you need much more of energy to break or denature the protein. So the delta G of denaturation will be much higher in a protein that has more disulfide interaction than in a protein that has less disulfide interaction. Okay. Questions? Okay. All right. So let's continue with the different levels of structures of the protein. So moving into the secondary structure. So the main secondary structure is alpha helix. So if you have a sequence or close to this sequence, polar, nonpolar. So P stands for polar, N stands for nonpolar. So if you have amino acid sequence of polar, nonpolar, two polar, two nonpolar, polar, nonpolar, etc., then your protein will most likely form an alpha helix structure. So the alpha helix structure has this axis here, and hydrogen bonds form parallel to the axis. The angle is almost zero. So they are stabilized in an alpha helix structure via hydrogen bonding that is parallel to the axis. And usually in a loop, in one turn, you have 13 atoms in one loop. That's what constitutes a alpha helix loop. The interior, again, like I said, is occupied by hydrophobic groups, given the fact that hydrophobic groups drive the formation of secondary structure. Again, here I'm reminding you is if this sequence is followed by proline, let's say, then you will lose that alpha helix structure, and you wind up having something called random coil. It's just a coil. And there's a lot of random coil in caseins, for example, which we'll talk about that later, because they have over 17% of their amino acids are proline. So you don't have that much of an alpha helix or beta sheet configuration in proteins that are high in proline. Okay. Beta sheet configuration is an alternating polar-nonpolar sequence of a protein will form beta sheet configuration. So you see here, like, you have sheets, and then the hydrogen bonds are actually perpendicular to the axis. So you'll say, are these different strands from different proteins or within the same protein? It's within the same protein. How does that happen? Is that you will have a protein here, and then it goes here. It could be a beta turn here, and then you will have this. So you will have hydrogen bonding here. So it's one molecule, and it has this beta sheet configuration. So at least two strands within one molecule form beta sheet. So the involvement is about 5 to 15 amino acids in a sheet. And if you have valine and isoleucine, you have a tendency to form, if you have a segment rich in valine and isoleucine, you have a tendency to form beta sheets. Beta turn is, like I said here, this is a beta turn. So, and the beta turn is basically composed of 4 units or 4 amino acids, and they're stabilized by 1 hydrogen bond, like this example. There are not a lot of beta turns in nature, not quite a lot, but they can definitely, beta sheet can convert to beta turn upon processing. Okay, you see this pattern a lot happening in dough formation and denaturation. So some of the beta sheet convert to beta turn depending on the composition of the protein. So because of processing or physical modification, you might get some beta sheet converting to beta turn. So what's so different, or what's the impact of having an alpha helix versus a beta sheet? So these are 2 different proteins. They are both whey proteins. So you have the albumin protein, and then you have the beta-lactoglobulin protein. If you look at the albumin, you see that it's a lot of the secondary structure of that protein is alpha helix. If you look at the beta-lactoglobulin, and it's called beta in this case, because of a lot of the beta sheets in its secondary structure. So beta sheets are more thermally stable than alpha helixes, and this is demonstrated by the fact that beta-lactoglobulin denatured around 75 degrees C, whereas the albumin denatures around 64 degrees C. So looking at the secondary structure, we can understand or explain the denaturation pattern. Okay, so when we talk about denaturation of the protein later on, we're going to refer to the structure of the protein and how they differ, and how that caused denaturation temperature to be different. So also, when heated in a solution, sometimes alpha helixes actually convert to beta sheet configuration. Okay. So moving from secondary to tertiary structure, which is the 3D organization of the protein itself, from primary, secondary to tertiary, and a lot of the tertiary structures are often stabilized by disulfide linkages. Okay? But that doesn't mean that all proteins have disulfide linkages, stabilization. So configuration of the tertiary structure is a function of primary structure and the secondary structure. So obviously the composition is a composition sequence, and then that will impact secondary structure, and the secondary structure and the composition together will impact the formation of a quaternary structure. So the tertiary structure is quite stable because at this point now, I don't know, we just have to go and recruit people that just want to come
That'll
into
be really fun. Every time they walk in.
Okay, so the tertiary structure is the most stable structure because at this point you have created all possible molecular interactions. So your entropy or your enthalpy is the largest, and the entropy is minimum. So you have the least chaos, you have the least amount of free energy, and most of your energy is contained in molecular interactions. So in a tertiary structure, you have all combinations of interactions taking place to form your final molecular structure or the tertiary structure of your protein. Okay. Here's two different structures, and due to their composition, they're very, very different. Okay. So beta-lactoglobulin is a globular protein. Beta-casein is an open structure protein. Beta-lactoglobulin has secondary structure. Beta-casein does not have secondary structure or has random coil mostly. Why? Because of the fact that it's high in proline. So why is it an open structure versus beta-lactoglobulin being globular structure? You have disulfide interactions within your beta-lactoglobulin. You have two disulfide bonds, whereas the beta-casein is lacking in disulfide linkages. So you have a very open structure, although you do have hydrophobic groups, but this is the case where I told you it's not always hydrophobic group are inside. There's not always inside and outside. And beta-casein does not exist as a single molecule. There is a quaternary structure. So caseins in milk are micelles. So the hydrophobic components that are really open like that are really still hiding from the aqueous because they're forming quaternary structures. And we'll talk about that more in the dairy section. Okay, so this is a globular and this is an open structure. This is stabilized by disulfide linkages. This does not have disulfide linkages. So there are differences in structure. And here's the quaternary structure that I was talking about. This is just a model, a theoretical model of a casein. There are different models. We'll talk about different models later. But the casein micelle is basically a combination of different proteins. You have kappa casein, alpha S1, alpha S2, and beta casein. They interact. Hydrophobic interactions occur in the middle of this quaternary structure, whereas most hydrophilic groups are on the outside of that micelle, where you have kappa casein that is glycosylated and negatively charged, or portions of it are negatively charged. So you have a net negative charge on the outside, allowing the micelle to stabilize within the milk and not precipitate out. So this is a quaternary structure in terms of different molecules of proteins are associating together to form a stable structure. And this is another quaternary structure, which is a hemoglobulin as well, is basically an association of 4 different molecules of proteins. There are other quaternary structures. Soy proteins form a quaternary structure, and we'll show that later on as well. So the quaternary structure is stabilized by the same type of bonding. Mostly it is non-covalent bonding. It's either ionic, hydrophobic, or hydrogen bonding is what stabilizes the quaternary structure. There are structures that are also stabilized by disulfide linkages, such as soy protein. Presence of water impact the formation of hydrogen bonding, so that plays a large role whether or not the structure is stabilized by hydrogen bonding. So other factors that contribute to the interactions are pH and ionic strength, and we'll talk about that with more examples for each type of protein. Okay, so I'm going to stop here. Next time we'll continue with different configuration of the globulars of the quaternary structure. Alright, so please take a moment and talk with your group partner about topics, and send me an email accordingly. Who left?
I'm gonna go.